Welcome to Nuclear Decay Videocast. Today we're going to be talking about nuclear decay, relating it to some the previous lab number 2 specifically, and also to give you an idea of the different types of nuclear decay that we have. The main ideas are: why are some atoms unstable? Why do we have nuclear decay? What is radioactive decay? And the third are the three types of decay: the alpha, the beta, and the gamma decay is what we'll be looking at today. So let's take a little review of the atom. Remember that our atom consists of two parts: the nucleus, which contains our protons, which are the red there, and we have our neutrons, which are the black balls, spheres right there. And remember that the number of protons that we have is called the atomic number. I'm going to be constantly saying that so I can get it fixed in your mind, that the number of protons that we have is called the atomic number. Now within the nucleus we have our protons and we have our neutrons, and outside of that nucleus are our electrons that are spinning outside of that. And if we add up our protons and neutrons, we get what's known as our mass number. And that's where I've been telling you to, when you're looking on the periodic table, to take that number that you see, the atomic weight there, and round to the nearest whole number, and that will give you the mass number. We're going to be using some data from our lab number 2, so hopefully you can see what is happening as we determine why are atoms unstable. Well, isotopes of any particular element contain the same number of protons but a different number of neutrons. This again is something that I'll constantly be reminding you of. All elements have isotopes. It's a particular element, has the same number of protons but a different number of neutrons. That's what an isotope is. And most of the isotopes which occur naturally are stable. It's when you get above atomic number 83 that you get the unstable nucleus. Remember from lab number 2 our data about protons and neutrons. The chart is at the lower bottom right of the screen there, and you can see where that cursor is. It's supposed to be a 1 there. So I'll put the 1 there so you can see that. And what this chart shows us is that your helium, carbon, your oxygen, they're in a 1-to-1 ratio of protons to neutrons. And then as they start getting larger, you can see that it's no longer a 1-to-1 ratio. And with the higher elements, such as uranium, you're getting to be at least 1 to 1.5 ratio of protons to neutrons. And that's when it becomes unstable. So small atoms, again, keep that 1-to-1 ratio. Our helium right here, our carbon, our oxygen, 1-to-1 ratio there. But the bigger atoms keep the 1 to 1.5 protons to neutrons. And you can see it's not necessarily with manganese here, but even with manganese it is starting to get to be a larger ratio than 1-to-1. So these unstable isotopes, what makes them unstable again is the number of neutrons that are starting to build up at a much faster pace than the number of protons that we have. And they have a 1 to 1.5 or greater ratio of protons to neutrons. Well, they become unstable, and the only way for them to get stable is by releasing different types of particles. And that's what we're going to look at, these different types of particles, the alpha, beta, and gamma emission. Well, this whole process of them releasing these particles is known as radioactive decay. So let's take a look at radioactive decay. It results in the emission of either an alpha particle, and we give it the Greek symbol there in parentheses, a beta particle, that is the Greek symbol for beta, also in parentheses there, or a gamma ray. So notice the first two are particles and the next one's a ray, and we call that a photon. So we're going to go over each of these a little in detail so you have an understanding of what an alpha particle is, what a beta particle, and a gamma ray is. Alpha decay is when you have a nucleus that in essence emits a helium nucleus. That is what an alpha particle is, a helium nucleus. So it's just like a helium atom without the electrons. So let's take a look at that. There are your two protons, there are your two neutrons. It contains the two protons, two neutrons, and what happens, we'll take an example here of radium-226, and it has the atomic number of 88. What happens in this case is by alpha decay, it will become radon, which has a atomic number of 86 and a mass number of 222. So remember, this 226 here, this is what we call isotopic notation. And I've written it on the board, but just for you to know, this is another way of us saying that this element right here, radium, has a mass number of 226, so the number of protons plus neutrons is 226, and the number of protons, or our atomic number, is written in the lower left region, and that is 88. So you can see the difference between these would be the number of neutrons you have, and would be greater than the 1 to 1.5 ratio that we're talking about. So if you want to shed weight, if a nucleus wants to shed weight, it's going to get rid of it by alpha decay, because you can see that that's a rather large particle. It has a mass number of 4, which is 2 protons and 2 neutrons, an atomic number of 2. And now keep in mind, as it goes down a chain, a radioactive chain, if you will, it can have more than just one type of decay. Alpha decay, beta, and gamma frequently occur. Next is our beta decay here, and a beta particle is a fast-moving electron which is ejected out of the nucleus of an atom that's undergoing radioactive decay. What's happening is that this nucleus is taking a neutron and converting it into a proton and an electron. So there's our nucleus, there is our electron beelining it, and beta decay occurs when a neutron changes into a proton and electron. So what does that mean as far as our mass number is concerned? Well, you can see here again, our mass number will stay the same, because mass number is number of neutrons plus protons, and what we're having going on with beta decay is a neutron is converting into a proton and an electron, so the mass number stays the same. However, you notice that our atomic number has changed. Our polonium here, PO, is going from 84 to our astatine here is 85. So we are gaining a proton. And in the process of that, we are also emitting a beta particle. So that's beta decay. Our last one is pure energy. They're not particles like alpha and beta, but it's pure energy. And gamma decay, a nucleus releases electromagnetic energy, but the isotope remains the same. So our mass number's the same, our atomic number's the same, the protons stay the same, the neutrons stay the same, as you can see in the table there. But it does emit a gamma ray. And that gamma decay, they're not charged particles like our alpha and our beta particles. And it's electromagnetic energy with high frequency, very, 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 very short wavelength, which relates to extremely high energy. When atoms decay by emitting alpha or beta particles to form a new atom, the nuclei of the new atom form may still have too much energy to be completely stable. So you may say, why is it doing this? Why is it releasing the gamma? Nothing's changing here. Well, that's an excellent question. Remember how I said that nature prefers a lower energy state. So this unstable nucleus is at a very high energy state, and in order to get to that lower energy state, it needs to release some energy, and in that process what it's going to do is release a gamma photon, gamma energy. And typically a gamma ray has an energy of 1 times 10 to the minus 12 joules, which joules is a source of energy, a unit of energy that we will be talking about in the future. Thank you for watching, and don't forget to do your summary.